Hey, Algebra 2. Today we're going to talk about graphing factored polynomials. So we're going to use the factored form of polynomials to find zeros of a function. And then we're going to use the factored forms of the polynomials to sketch the components of graphs between zeros. Notice I said sketch. Okay, sketch is a do our best to make it look like it should, but it does not have to be very precise. Okay, let's go. First of all, an engineer is designing a roller coaster for younger children and has tried some functions to model the height of the roller coaster during the first 300 yards. She came up with the following function to describe what she believes would make a fun start to the ride. It's h of x equals negative 3x to the fourth power plus 21x to the third power plus 48x to the second power. Sorry, I meant negative 3x to the fourth plus 21x to the third minus 48x squared plus 36x, where h of x is the height of the roller coaster in yards when the roller coaster is 100x yards from the beginning of the ride. Answer the following questions to help determine at which distances from the beginning of the ride the roller coaster is at its lowest height. So let's go through these questions. Does this function describe a roller coaster that would be fun to ride? Explain. The roller coaster quickly goes to the top and then drops you down. This looks like a fun ride. So I graphed this equation with my graphing calculator. Let me import some pictures so we can see what just happened. First of all I did was push the y equals button below the screen in my calculator, and I typed in the equation that you see right there. Okay, let me show you something else. Alright, what you see up here, I just set the window scale. So I pushed this button right there, and then I did my x min was -2, my x max was 5. So if you look at the x-axis, I went from -2 to 5. And the y's I just kept -10 to 10, which is fine. And I like my scale as 1. That means that each tick mark is 1. That's awful. And then I just hit the graph button, and you'll see the graph there. So now that we see the graph, we can tell sort of what's going on. So to me it looks like this roller coaster quickly goes to the top. We see it quickly goes to the top and then drops you down, and then a little bit up, and then all the way down. Looks like a lot of fun. But if you like roller coasters that go nearly straight up and then all the way back down. Okay, let's move on with our slides. So at height 0, it looks like we're from, 1, 2, 3. Height 0 when x equals 0. Height is 0 when x equals 0. At that value, each term is equal to 0. So the height is 0 when x equals 0. So our equation going in, each term is equal to 0 when x equals 0. If you look at the equation, you have the equation in front of you. There's an x at every term. There's no constant. All right, can you see any obvious x values from the equation where the roller coaster is at height 0? I'm going to go back. So your height equals 0 when x equals 0, which is, each term is 0. Using a graphing utility, graph the function on the interval from 0 to 3. And if you look at the x min and the x max that I used, let me look. I went -2 to 5. So I should have kept that at 0 to 3. So I'm actually going to change mine and look at it again. So for part C, oh goodness, I set the X interval from 0 to 3 and identify when the roller coaster is 0 yards off the ground. So between 0 and 3, the X value satisfies if we do h of x equals 0. That occurs at 0, 2, and 3. So when x is 0, 2, and 3, that would be when the roller coaster is 0 yards off the ground. So what do the x values you found in part C mean in terms of distance from the beginning of the ride? So the distance represents 0 yards, because remember, distance from the beginning of the ride was 100x. So if I plug in 0, I would get 0 yards, 200 yards, and 300 yards. Very cool. All right, why do roller coasters always start with the largest hill first? They need speed. So they can build up speed from gravity to help propel the cars through the rest of the track. Without any speed, they would never make it up the next hill. Verify your answers to part C by factoring the polynomial function h. Let's try it. H of x equals negative 3x to the 4th plus 21x to the 3rd, 48, 48x squared plus 36x. There's a common factor here. I'm going to take out a 3x, negative 3x. I'm going to be left with x cubed, 7x squared minus 16x. Oh, I have to change my signs. Hold on. Minus 12. Okay, I took out a negative. That means that this is wrong. And this is wrong. There we go. I think we're good. Minus, plus, minus. Yep. All right. Can I do anything else? From the graph, we actually know some of our zeros. We got 0, 2, and 3. So that would mean x minus 2 and x minus 3 and x are going to be some of our factors. So let's actually use that to our advantage and do some long division. I'm going to divide x minus 3 out of this mess. And I'm going to push pause because I don't think you need to see me long divide. I'll be back in a second. All right, getting a little crowded. So I have negative 3x. I have x minus 3, which is correct, and I just divided that. I'm left with x squared minus 4x plus 4. So I can factor that last. Actually, I can't. Pause. Let me erase this. Okay, that trinomial I can't factor. Okay, it doesn't quite work out. Oh yeah, it does. Okay, sorry. So let's try that again. So negative 3x, x minus 3, and this goes to x minus 2, x minus 2. So now we have all of our answers. Okay, this first term gives me x equals 0. The second is x equals 3, and the last two are x equals 2, multiplicity of 2. Okay, verify your answers to part C by factoring the polynomial. Check. So how do you think the engineer came up with the function for this model? It's quite complicated, but basically to start at height 0 and end 300 yards later, this was 1, 2, 300 yards later at height 0, she multiplied x times x minus 3 to create zeros at 0 and 3. Okay, I'm going to erase that because I need the space. To create the bottom of the hill at 200 yards, she multiplied this function by x minus 2 squared. And then she needed to multiply the whole thing by -3 to guarantee the shape. That -3 guarantees that you go up first before you go back down. Okay, that's what the leading coefficient of a negative does. That right there. Okay? What is wrong with this roller coaster model at distance 0 yards and 300 yards? So what is wrong at distance 0 and 300? Why might this not initially bother the engineer when she is first designing the track? So the model appears to abruptly start at 0 yards. Okay, there's no, I guess we're not including this part. How does it get there? And abruptly ends at 300 yards. The fact that the roller coaster looks as if it will crash into the ground at 300 yards. The engineer may be planning to smooth out the track. So when you have your graph, it doesn't start here and then stop there. You know, the engineer is going to smooth out the track so that it'll come to a rolling stop and maybe put some padded brakes here, slow it down. And I don't know if you guys have been to Silver Dollar City, but it's like a powder keg where it shoots you off like a cannon. This one will have, you know, some tracks that will carry it up before it lets it go down. Pretty cool. Okay, graph each of the following polynomial functions. What are the function's zeros, counting multiplicities? What are the solutions to f of x equals 0? What are the x-intercepts to the graph of the function? How does the degree of the polynomial function compare to the x-intercepts of the graph of the function? So here we have f of x equals x times x minus 1 times x plus 1. We know the zeros are 0, 1, and -1. Okay, the solutions to f of x equals 0 are also 0, 1, and -1. You know, I'm going to write those in a different order. -1, 0, and 1. -1, 0, and 1. The x-intercepts are also -1, 0, and 1. The degree is 3 because I have 3 x's. So if I multiply that out, it would be to the 3rd degree. And if the degree is 3, which is the same as the number of x-intercepts. So, hold on, I'm going to make that a little thicker so we can see. There we go. Very nice. Cool. Let's see what we can do. Make that thinner again. See how that works. So let's graph our zeros. I'm going to say that's -1. 1, 2, 3, 4. 1, 2, 3, 4. Because I don't want it to be too crowded. 1, 2, 3, 4. 1, 2, 3, 4. Okay, our zeros were at -1, 0, and 1. Okay. Okay, at this point, I get my graphing calculator out and I push the y equals button. And I type in exactly what I see here. And then I hit the graph button. You may have to change your window. I set mine at an x min of -5 and an x max of 5. And that gave me a general shape. Yeah, let's try that again. Like that, okay? It's a general shape, okay? We knew that it would cross the x-axis at -1, 0, and 1. So we knew the general shape. A third degree is always going to have a shape like that, but we'll get used to that as time goes on. Let's try the next one. All right, so let's graph this one. Let me get x, oh, I don't want it red, sorry. Do your best, right? We're sketching. Let's make that skinny again. So what do we have here? I have my zeros at -3, -3, -3, and -3. I have my solutions at -3. I don't have to repeat them. X-intercept is just 1 at -3, and my degree is 4. Notice I have a 4th degree, which is bigger than the number of x-intercepts. Yikes. Okay, go ahead and type it in your calculator. I'm going to push pause and do the same thing. Okay, 1, 2, 3. This is -1, -2, -3. So our graph looks something like that, right? So here we have a 4th degree, and our graph looks pretty wide at the bottom. That's awful. That was what our graph looked like. Okay, our 3rd degree looked like that. 2nd degree looks pretty similar to the 4th degree, but we'll get to shapes as we learn. All right, let's try another one. We have all of our answers. I have my zeros. I have a 0 of 1, 2, I can't see that. Hold on, let me get my student book out. There we go, 1, 2, -3, -4, and -4. But you know what? We need to list those in the right order. So let's do it right. -4, -4, -3, 1, and 2. All right, our solutions are -4, -3, 1, and 2. Our x-intercepts are -4, -3, 1, and 2. And our degree equals 5, which is greater than the number of x-intercepts. Okay, let's see if we can graph it. I'm going to push pause, okay? Okay, I have x-intercepts at -4, -3, 1, and 2. If I look at the graph that I did, looks like we come up, touch here, down, all the way up. Oh my goodness, let's try that again. We have a problem now. Okay, this should go down much further before it comes up. That's hard to draw freehand, isn't it? Okay, so we have a fifth degree, which we sort of came up, touched way up, way down, and back. Okay, if that makes sense. Oh, that last thing I drew is not right. There we go. Okay, that was my fifth degree. D, let's try it again. So my zeros, all are 2 and 3. My solutions are also 2 and 3. My x-intercepts are 2 and 3, but the degree is 4. Okay, hold on, I need to move this. I'll move it back in a second. Okay, this right here solves for x squared equals -1, square root of both sides, x equals square root of -1, which is not real. So I can't include it. I know that can be frustrating, but can't include it. We can only include the real ones when we're graphing. Let's put that back up there. All right, let's see how we can draw it. I'm not going to type it into my calculator here in a second. I know my zeros are at, let's do 2, 1, 2, 3, 4. All right, hold on a second. So I'm going to cross here and here. Take a little loop. Okay, pretty funny looking. All right, so we talked a little bit about why the factor of x squared plus 1 is not a 0, because it gives us an imaginary number. It's not real. So for real numbers x, the value of x squared is always greater than or equal to 0. So x squared plus 1 will always be strictly greater than 0. So x squared plus 1 can't equal 0 for all real numbers x. Since there can be no x-intercept from this factor, the graph of f can have at most 2 intercepts, which is what we had. Cool? Okay. All right, example 2. Okay, consider the function f of x equals x cubed minus 13x squared plus 44x minus 32. Use the fact that x minus 4 is a factor of f to factor this polynomial. So I'm going to do some division. X minus 4 to figure out the rest of it. So I'm going to go ahead and push pause, and we'll factor this for us. Okay, I found the x-intercepts for the graph. Okay, they're right there. Check out the factoring if you need a little help, but those are the x-intercepts. They should be listed smallest to biggest, but not a big deal. At which x values can the function change from being positive to negative, or from negative to positive? Only at those x-intercepts. So that's where your graph is going to change. That's where we get loops up and down. It can only change at the x-intercepts. Okay, let me erase that and write down the answer. So only at the x, oh for goodness sakes. Only at the x-intercepts can the function change from being positive to negative, or from negative to positive. To sketch a graph of f, we need to consider whether the function is positive or negative on the 4 intervals from x is less than 1 to between 1 and 4, between 4 and 8, and then bigger than 8. Why is that? Since the function can only change at the x-intercepts, the graph's going to always be above or below the axis. So the function can only change at those intercepts. So the graph will be above or below the axis at those intercepts. How can we tell if the function is positive or negative on an interval between the x-intercepts? Well, we can evaluate the function. We can evaluate the function at any point between those intervals. So the function's either positive or negative. We can check a single point and it'll tell us what's going on. So evaluate, so check any point really between the intervals. We'll do this next. So for x is less than 1, is the graph above or below the x-axis? So we really need to just pick a number less than 1. 0 is the easiest because it's really easy to plug in 0. If we do that to our original function, which I need to pull out that original function, we have f of x equals x cubed minus 13x squared plus 44x minus 32. So f of 0 is negative 32. Okay, that's how we can tell. So we're negative. So the graph is below the x-axis for x is less than 1. How about between 1 and 4? Okay, so let's pick a number. 2 is usually easy to work with. So f of 2, if we plug in 2, we would have 8 minus 4 times 13. You guys are probably faster in your head. I've got 12, 22. 8 minus 22 plus 88 minus 32. That should be 52. Not sure what I was thinking there. That's 52. That gives me an answer of 12. So it's positive. Cool. Moving on. I hope you're keeping track of all this stuff. Between 4 and 8. 5 is usually easy to work with. Let's see, we have 5 cubed, which is 125. 25 times 13. 325. Then we have 5 times 44. Plus 220 minus 32. 125 minus 325 plus 220 minus 32. I have negative 12. And that is negative. For x is bigger than 8, 10 is usually easy to work with. So 10 cubed minus 100 times 13 plus, what's next? 440 minus 32. Let's see if I did that right. Minus 1300 plus 440 minus 32. I got 108. Cool. 108 is positive. So we know the direction on each interval of the graph. So let's graph it. I hope you guys are taking good notes. All right, my zeros were 1, 2, 3, 4, 1, 2, 3, 4. Oh, dang it. Graphing can be the hardest. It's always good to check your zeros before you start. So we have 2. And we don't want to do that. So we have 1 at 2. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. Cool. I hope you can read my graph. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No. I went by 1. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so where x was less than 1, we were negative. So we're going to start low, and then we were positive, and then negative, and then positive. Okay, so we know the general shape of the graph. So on the interval from 0 to 9, on your graph, on your graphing calculator, see if you can get the same picture. So I'm going to pause and try it. All right, I went from 0 to 9, but I also went from, let's see, negative 20 to 15 to try to get the minimum in there. So I sort of made it. They look pretty similar. I think we did a great job. All right, did it. Check. Right, for any particular polynomial, we can determine how many relative maxima or minimum there are. Can we determine? Consider the following polynomial functions in factored form and their graphs. So for here, like I have the degree. So I have 2, 1, 2, 3, 1, 2, 3, 4. Okay, number of x-intercepts, I have 2, 3, and 4. The number of relative maximum and minimum points in each graph, I have 1 minimum. I have a maximum and a minimum. I have minimum, maximum, minimum. Yeah? What observations can we make from this information? The number of relative maximum and minimum points is 1 less than the degree and 1 less than the number of x-intercepts. So the number of relative, the number of relative maximum and minimum points is 1 less than the degree and 1 less than the number of x-intercepts. Cool. Let's try some more. Okay, the degree, I've got 2. I have 3. I'm getting this from right there. And 1, 2, 3, 4. Number of x-intercepts, none. I've got 1 and 1, 2. The number of relative maximum and minimum, I have 1. Ooh. 1. And now I really can't see 1 in that last one. So it really doesn't have a maximum or a minimum. And 1 right there. So what observations can we make from this information? Basically, the observations we made last time do not hold true. So really, it's really difficult to say, to determine from the degree of the polynomial function. So where are we at with degree? So from the degree of the polynomial function, the relative number of maximum and minimum. So basically we can say for n degree, we will have at most n minus 1 maximum and minimum. You can also think about the information you can get from a graph. If a graph of a polynomial function has n relative max and min points, you can say the degree would be n plus 1. Okay, you can make that backwards. Okay, relevant vocabulary. Go ahead and read through these. It's some things that we did and did not deeply cover in the lesson. We talked a little bit about it and continued. And then lesson summary. A polynomial of degree n may have up to n x-intercepts and n minus 1 max and mins. Okay, that's the last thing we just talked about. The plural of maximum is maxima, and the plural of minimum is minima. You know, yay. All right, we'll see you guys tomorrow.